So welcome back, students. We've already seen the Bohr's concept, isn't it? So I've taught you how Bohr has given us the explanation for hydrogen atom, isn't it? So we have seen Lyman series, Balmer, Paston, bracket, P-fund. Now let us solve the numericals based on Bohr's model. Fine. So this is not a grade 10 Bohr's model. Very clearly I've mentioned the method to calculate radius and energy of the orbit. Please watch the video, then only come to this concept. Fine. So let's read the question. What do they give us? What is the wavelength of light emitted when an electron in a hydrogen atom? So they are speaking about hydrogen atom. You need to remember the formula. Let's write that. Undergoes transition from energy level n is equal to 4 to energy level n is equal to 1. So my request is, before solving the numericals, try to watch the earlier video. Then only you will understand what am I trying to speak. Yes. So now while solving the numerical, first important thing, let us divide the board into two equal halves. Let us write what is given, what to find out, what is the formula. For everything, every part carries mark. First of all, in the given question, first of all, what should I find? What is the wavelength? So I need to find wavelength. Then what is given when the electron in a hydrogen atom undergoes transition from energy level n is equal to 4. So n is equal to 4 and to energy level n is equal to 1. So it's dropping down, it seems. Fine. So lambda, how to find out? But here from the formula I have two relations. What are they? With this data I can write a formula that is nu bar, that is centimeter inverse, is equal to Rydberg's constant into 1 by n1 square minus 1 by n2 square. This is the formula which you have learnt in hydrogen spectrum, which was given by Bohr. Yes, fine. So what is Rydberg's value? I'll write that Rydberg's value also. We know Rydberg's constant is equal to 109677, isn't it? Yes. So substitute that. Nu bar is equal to 109677. Yes. Now what is n1 in this case? It is 1 by 1 square minus n2 in this case 1 by 4 square. When I solve this particular thing, when I solve this whole, take the LCM, solve it and multiply this. So you get an answer of nu bar is equal to okay, this is all centimeter inverse, isn't it? Yes, 1028222 centimeter inverse. I'm still not done. I need to find out. So what is the relation between wavelength and wave number? We very well know wave number is inverse of wavelength. This is what we have studied earlier, isn't it? So I already have the wave number with me. I'll substitute in this formula. So substitute nu bar is equal to 1 by 102822 centimeter inverse. When I solve this, I get an answer of, okay, no, we have written something wrong, isn't it? Yes. What is the mistake? We should write lambda is equal to 1 by nu bar. This is the concept. We have written reverse. So wavelength is equal to 1 by nu bar. So lambda is equal to 1 divided by 102822 centimeter inverse. When I solve this, I get an answer of 9.7 into 10 raised to the minus 6 centimeter goes above, this becomes centimeter. Further, if I have to convert into nanometer, you can multiply this with 10 raised to the 7 nanometer, isn't it? Yes. So lambda I get equal to 97 nanometer. Fine. So just simple. You've taken that out. 7 plus 6 minus 6 and plus 7, that becomes 1, and finally you've shifted one decimal and you get finally 97 nanometer. This is how we are going to solve the numerical. Right. Now let's come back and do one more numerical based on the same concept. Fine. So here what do they give us? Calculate the wavelength of the first and the last line in the Balmer series of hydrogen spectrum. So what do we learn in hydrogen spectrum? We have learned the first line is Lyman series. Then comes the Balmer series. I also showed you the spectral lines. How are they going to shift from the ground state, that is Lyman, it's going to from N1. And Lyman starts from N1 is equal to 1. Balmer starts from N1 is equal to 2. That is what I said. So when Lyman is N1 is equal to 1, it's going to go to 2, 3, 4 like that. When it is Balmer, N2 is equal to 2, it's going to get excited to 3, 4, 5 like that, isn't it? So that they are now speaking about Balmer series. I'm again mentioning, before you watch this video, go and watch the previous video that is for hydrogen spectrum. Unless until you understand the concept, it is meaningless doing numericals. Yes, fine. So in this particular numerical, what should I find out? First of all, right, I need to find lambda. Yes, for which one? For the first line and the last line, and that too for which series? Balmer series. So for Balmer series, N1 is equal to, if I have to say, it is 2. Lyman it is 1, Balmer is 2. Fine. So for the first line, this is from, this is already the ground state. From here, where does it get excited? You should see the first line. Now from this N2 level, it's going to go to this N2, N is equal to 2. It's going to go to N is equal to 3. So the first line would be N is equal to 3. Fine. So next one, I need to find for the last line also. Now N is equal to, N1 is equal to 2 always. That's the ground state for Balmer. And N2 for the last line, if they say, it is infinity. We can't predict, isn't it, in that? So that is infinite value. Now substitute in the formula. So according to the formula, I need to find lambda. That means 1 by lambda I can write, isn't it? Yes, because nu bar is nothing but inverse of lambda, wavelength. So 1 by lambda is equal to 109677 Rydberg's constant into 1 by n1 square minus 1 by n2 square. Now substitute the values in this. 1 by lambda is equal to 109677 by 2 square minus 3 square. So when I solve this, how much do I get? I get an answer of 15232.9 centimeter inverse. But still there is 1 divided by, isn't it? So when I divide this 1 divided by, I get an answer of 6.565 into 10 raised power of minus 5 centimeter, because this goes above. So I've already written the answer, so that's easy for me to take it. Now the same case. In this case, 1 by lambda is equal to 109677. So 1 divided by 2 square minus 1 divided by infinity, because that's the last line. Now substitute. So 1 into, when I solve this whole thing, I get an answer of 2741.9.3 centimeter inverse. So lambda is equal to, when I divide this by 1, I get an answer of 3.647 into 10 raised power of minus 5 centimeter. Earlier it was in the denominator, so centimeter inverse. Now come to the numerator, this becomes centimeter. So this is your first, this is for the last line, that is, which they've asked me, last line, and this is for the first line. So see, all the units are similar. Here also in centimeter, here also in centimeter. Finally, you have ended with lambda. Here also you have ended with lambda. So this is how you're going to do the numeric. Right. Now let's come back and do one more numerical, which is based on Bohr's hydrogen spectrum. So here what do they give us? Let's see. So whenever you're doing a numerical, try to read the numerical completely, write the given data, write the formula, and then substitute it. It's easy. So here what they give us, applying Bohr's model. Okay, I need to apply the Bohr's concept, calculate the wavelength of the radiation, right? I need to find wavelength, okay, emitted when an electron in an hydrogen atom makes a transition from 4th energy level to 1st energy level. Okay, there are 2 energy levels. So what did you do it from? It has first excited, it has absorbed 1 photon of energy from N1 is equal to 1. It has got excited to the 4th energy level. After some time, it has lost its energy, and it has, from the excited state, it has come to ground state. Okay, fine. So I need to calculate wavelength. So simple. So we've already written the formula 109677 into 1 divided by n1 square minus n2 square. But here you have to be careful. Why? Because I said energy levels. According to Bohr's model of an atom, energy for the nth orbit, right? What is the formula we have learned? It is equal to 2.18 into 10 raised power of minus 18 divided by n square. This is what you've studied, isn't it? Joule per atom. Fine. Right. So they've given us two energy levels now. One is N1 is equal to 1, N4, okay, means N is equal, for the first one, N is equal to 1 for 1 and N is equal to 4. I need to substitute in this formula. So when you substitute, En is equal to 2.18 into 10 raised to the power of minus 18 joule per atom, 1 square for the first one, fine. And for the second one, E, that is the next level, 2.18 into 10 raised to the power of 18 joule per atom by 4 square. Fine. So basically they have two levels, transition. So when there is a transition like this, individually this is energy of this particular orbit and this is the energy level formula for calculating this particular orbit. Now when they say there is a transition from the fourth energy level to the first energy level, I can also write this formula as, yes, how can I write? En, okay, this is equal to 2.18 into 10 raised to the power of minus 18 into 1 by the first one, 1 square minus 1 by 4 square. Why did I write this formula? Because this delta E is equal to E1 minus E4. Isn't it? Change, because it is getting transit, means there is a transition from the fourth to the first one. Individually this is nth orbit, and when it goes to the transition you need to consider this formula. So when I calculate this, I get delta E. How much do I get? I get an answer of minus 2.04 into 10 raised to the power of minus 18 joule per atom. This is the first one, but still the numerical is not done. Why? Because they've asked me to calculate lambda. Now let us erase this and come back. So I'm going to erase this whole part A thing and come back to the next one, but I need to have the answer with me. Fine. So now I'm calculating the part B. I've got E value. How much did I get? I got minus 204 into 10 raised to the power of minus 18 joule per atom. Now simple, isn't it? We already know the formula. E is equal to H nu. What is nu equal to? C by lambda. Our lambda is here. Now substitute this formula here. This becomes E into nu is C by lambda. I want this lambda out. Take this and cross multiply. What do you get? HC by E. Simple, isn't it? Now start substituting. What do I know? Planck's constant is already given to me. Lambda is equal to 6.63 into 10 raised to the power of minus 34 joule second is given to me, into, right, c, velocity of light, that is 3 into 10 raised to the power of 8 meters per second, divided by del E. How much did we get? We've got minus 204 into 10 raised to the power of minus 18 joule per atom. When I solve this lambda value, I get an answer equal to 9.7 into 10 raised to the power of minus 8 meter. Further, if you wish to write it in nanometer, shift one decimal in this direction. This becomes 97 nanometer. That's it. So simple, isn't it? Solve the numerical in 2 steps. See what is given. First go with the basic level, basic energy level. Then transition means subtract both, get the energy level, substitute in this formula. Then finally get that lambda, and the final answer is this. Right, now let's come back and solve an NCERT numerical which is based on the Bohr's hydrogen spectrum. Let's see this. Here what do they give us? Calculate the wavelength for the emission transition. Okay, if it starts from the orbit having the radius of, okay, they've given us radius here, one radius, that is 1.3225 nanometers. One radius is given in nanometers, and ends at 211.6 picometer. So both are given in different units. You need to convert that. Fine. So now next is name the series to which the transition belongs. Okay, they want us to tell whether it is Lyman series, Balmer, Paston bracket, or P-Fun. Fine. And the region of the spectrum. Okay, they have given us 2 tasks. One, I need to tell them which series it belongs. Point number 2, I need to tell them in the spectrum, does it belongs to visible spectrum, infrared or ultraviolet, or gamma or radio waves. Let us calculate the formula. Okay, let us calculate this. How to do this? First of all, when such numerical is given to you, write the given data given, like note the given data. What do they give me? They've given us radius is 1.3225 nanometer. Fine. One more radius which is end. Okay, let us write this as R1. Let us write this as R2. Here ends at 211.6 picometer. Now convert this into picometer. This becomes 13.225 picometer. Is 5 picometer. Fine. Right. So now we have a formula that is radius for nth orbit. So what is the formula? It is equal to 52.9 n square by z. This is the formula which we have learned. Now I'm given two radius. Relate to this formula. Take the ratio. How to do this? It is nothing but, see here. For the first one, if I take for the first one, this becomes R1 is equal to 52.9 n1 square by z. For the second one, if I take R2 is equal to 52.9 n2 square by z. Yes, so Z for hydrogen-like species is, like if you take the hydrogen atom, they've taken hydrogen atom, then it's 1. Both the cases it is 1. Now what am I left with? I'm left with R1 by R2. How much did I get? The value for R1, it is 1322.5 picometer. R2 is 211.6 picometer, which is equal to your n1 square by n2 square. Now when I solve this, I get an answer of, okay, n1 square by n2 square, I get an answer of 6.25. If I take out the square root, n1 by n2, I get an answer of 2.5. Further, if I take out the decimal, n1 by n2 is equal to 2.5 by 10, nothing but 5 by 2. Now what did we get? We have got n1 value equal to 5, n2 value equal to 2. This is what is the concept. Now n1 value equal to 5, that means from where did it go? It has gone from, look here, from second level n1 it has gone to the next level, from second to third, the second to fourth, second to fifth, right? So it has dropped down from the fifth orbit to the second orbit. It's clear, isn't it? Yes. So once again, it has started from the second, third, fourth, fifth. From fifth, it has again come back to second. So which series does it belong? Lyman belongs to n is equal to 1. Balmer belongs to n is equal to 2. So we have got the first answer. The series which it belongs to is, the series is Balmer series. That is over. Fine. So I have got one answer. Now I need to find the region, to which region it belongs to in the spectrum. So let us erase this part of the board and come back. So here to find the region, you always go with which formula? That is Rydberg's constant. That formula, that is nothing but nu bar, or it is equal to 1 by lambda is equal to 109677 into 10 raised to the power of -7. So 1 point it will become there, into 1 by n1 square minus 1 by n2 square. Now here you have to be careful. What is the ground level? Earlier when I took the formula, when I got n1 is equal to 5, n2 is equal to 2. But now, which is the ground state? Basically, yes, its ground state is always the lower one, Balmer series. So here there will be a change, remember that. So lower is 2, the higher is 5. The other way, when you see from 5 to 2, that's different. Here lower is 2. So substitute 1 by lambda is equal to 1.09667 into 10 raised to the power of -7 by 1 by 2 square by 1 by 5 square. When I solve this, I get 1 by lambda is equal to 2.303 into 10 raised to the power of -6. When I solve this this fraction, lambda, I get an answer of 0.434 into 10 raised to the power of -6 meters. Okay, still I am not done. Fine. So convert this further into your nanometers. So if I convert this into nanometers, I already gave one formula initially how to convert the different units of nanometers. This becomes equal to 434 nanometers. Yes, so lambda I've got it in 434 nanometers. Hope you know the conversions from meter to centimeter, centimeter to nanometer. Fine. So now I need to answer this question. What region of the spectrum? So we very well know our visible region, it starts from 400 nanometers to almost 750 nanometers. So where is it lying? It's lying in 434 nanometers range, isn't it? So according to this, so what did I just now said? Visible region starts from 400 nanometers to 750 nanometers. So this is lying in between this. So the answer would be the region observed is visible region. So once again, let me conclude. I have got two important things. One is I took the first formula, that is the radius formula. Fine. After taking the radius formula, I took the ratio. From the ratio, I got the first thing, that is series. The series which it belongs is Balmer series. Fine. So n is equal to that, n1 is equal to 5 and n2 is equal to 2. After that, I got the what is that region in the spectrum. How did I do this? I took the wave number or the wavelengths in this, and I finally substituted, and finally I got an answer, that is 434 nanometers, which is in visible region. That's it.